Okay, I see the recording sign on. So welcome everybody. This is Giuseppe Santoro from CISA in Trieste. We are ready to start session 2 of this virtual conference on quantum annealing, adiabatic quantum computation. The first speaker today is Daniel Lidar. He needs no introduction to everybody here in the audience. And I just remind you that in 2 hours and 15 minutes, so at the end of the live talks, there will be a recorded version of Professor Nishimori talk in session 1. So from, say, 8:15 local time here in Rome to 9, okay? So I would start with Daniel Lidar from University of South California. Please, Daniel, you can start.
Thank you. Can you see my screen?
Yes, I can see it.
Great. Okay, well, thank you, organizers, and thank you everyone who's tuning in now and who's tuning in later. I would like to tell you about the achievements of the IARPA, QAO, and DARPA crafts programs, and also talk about the prospects for quantum enhancement with quantum annealing, which is joint work with Elizabeth Crossan on the archive. So it's been a decade since the DWave 1, and it's a time to ask the question, where does quantum annealing stand? Well, we've had numerous studies that have attempted to demonstrate speedups using the DWave processors. And in some cases, we've had examples of constant factor speedups in optimization. That is against all classical algorithms that were tried. And in other cases, we have had claims of a scaling speedup for quantum simulation, speedup against path-integral Monte Carlo in the context of geometrically frustrated magnets, where the problem was the scaling of the relaxation time in escape from topological obstructions. So these are very impressive achievements. Now, I will not talk about simulation today. I want to focus on optimization, even though simulation is, of course, a natural and promising application for quantum annealing. Quantum annealing was originally proposed as an optimization heuristic, and that's going to be the focus of this talk. And unfortunately, so far, there has been no study that has demonstrated an unequivocal scaling speedup as opposed to a constant factor speedup in optimization. The closest we got was this work from a couple of years ago, which focused on finding the ground states of a family of planted solution spin glass instances. And in this work, what you're seeing is the time to solution as a function of the problem size. There was a certifiable scaling speedup, certifiable because an optimal annealing time was identified for the DWave 2000Q against simulated annealing with a scaling exponent that was within within the error bars. So this was encouraging, but unfortunately, when you compare against more sophisticated classical algorithms, specifically in this case, spin vector Monte Carlo and simulated quantum annealing, the scaling speedup disappears, and simulated quantum annealing has a scaling exponent that is about a factor of 2 better than the one that we found on DWave. So this type of result begs the question, what is the reason for the lack of the scaling speedup? And there are several possibilities. Perhaps quantum annealing is just an inherently poor algorithm. I'll talk much more about that later. Control errors might be the culprit. Well, it's known that J-chaos errors have a strong detrimental effect. In fact, they limit the size of devices that can be expected to accurately solve optimization instances if you don't do any error correction or error suppression. And of course, there's decoherence. The single qubit T1 and T2 times for the DWave devices are a lot shorter than the anneal time. And that is often cited as a major problem of quantum annealing, at least relative to the gate model. The importance of the decoherence story is complicated. It depends on whether there's a weak or a strong coupling to the environment, and I'll talk much more about this later as well. But in any case, reducing noise via better engineering is undoubtedly a good idea, and that is borne out when we re-studied the set of problem instances that I just talked about from 2 years ago on the new lower noise DWave 2000Q. Once again computed time to solution as a function of annealing time. And whereas in 2018, the report was for the largest problem size of 2048 qubits, and an optimal anneal time at about 40 microseconds, that's the red dot here. For the same set of problem instances, up to a slight tweak, on the new 2020 low noise machine, we found that the time to solution actually kept going down as a function of anneal time, and no minimum was discernible even at the lowest anneal time of 1 microsecond. So clearly an improvement due to the lower noise characteristics of the new device. So these results with lower noise are encouraging. If we focus on this aspect along with the lack of scaling speedup in optimization so far, this justifies a reevaluation of the prospects of a quantum enhancement using the traditional quantum annealing approach. And here by traditional, I mean DWave's qubit design. And I think we're going to hear more about that in the talk by Andrew King later in the session. And the idea of adiabatic quantum annealing with forward annealing paths. So for the rest of this talk, I want to talk about two things. One is the emphasis on coherence, which is the approach of the QAO program. And secondly, the critical evaluation or reevaluation of the adiabatic versus diabatic and the forward versus reverse quantum annealing approaches. So let me start with part one, which is the emphasis on coherence. And that is the approach of the QAO program. So what is the QAO program, first of all? It was a program that was started by IARPA officially in June 2017, lasted until February of this year, and actually was replaced by a new DARPA program called QAFS, the Quantum Annealing Feasibility Study. And that is slated to last until August of next year. In both cases, the goal is essentially to evaluate the prospects for quantum enhancement via high coherence and high control quantum annealing. Briefly about the team itself, it's composed of three sub-teams: the so-called performer, the government furnished capability or GFC, and the test and evaluation, the TNE. The performer flux team, of which I'm the PI, has about 100 researchers from 10 different institutions. The institutions are listed here. It's an international collaboration. The government furnished capability is at MIT Lincoln Lab, and they do all the fabrication for this program. And the test and evaluation team is centered at NASA Ames, headed up by Eleanor Eiffel, who will also give a talk in this session. So there's a lot to say, obviously, about this program, and I want to focus on a few highlights. So first of all, let me contrast the DWave versus the QAO type flux qubits. And let me focus specifically on architecture and the question of persistent current. So in terms of architecture, in the DWave case, the qubit physical layer is integrated with the classical control layer. In the QAO approach, the qubit physical layer is separated from the classical control layer via a 3D integrated shielded signal routing approach. This is designed to isolate the qubits and hence hopefully increase coherence. And there's a schematic here with the qubit and layer separated from the classical control layer down here through an interposer. In addition, in the QAO case, we have designed the chips so that we have time-dependent control of every qubit and every coupler bias, the H's and the J's, from room temperature. As for persistent current, the DWave qubits have a relatively high persistent current, about 2.5 microamps. But a useful heuristic is that the T1 and the T2 times both scale inversely with persistent current. So you'd expect that high persistent current will lead to a relatively low coherence time. And just recently, we've had a measurement reported of T1 and T2 of about 16, 17 nanoseconds in the DWave qubits. The QAO so-called capacitively shunted flux qubits, the CSFQs, have a lower persistent current by about a factor of 10. And both T1 and T2 have been measured to be about 100 times larger than the ones reported so far by DWave. So here is an example. The T1 as a function of persistent current. What you're seeing here are the results reported by DWave, by Google, and by Qaoa. And here's the actual measurement of one of our 4th generation chips with a T1 of 3.5 microseconds. We also measure T2, of course. And so here's an example of the same 4th generation chip with a T2 measured at the symmetric double well or flux insensitive operating point, 130 nanoseconds T2 star. And if you measure at the so-called saddle point, the double flux insensitive operating point, we found a T2 of about 4.5 microseconds. So the summary is the CSFQs so far, at least in the so-called single tier devices without the interposer, have consistently demonstrated a T2 at the saddle point well over 1 microsecond. Assuming that our anneal times are going to be on the order of about a microsecond, this is encouraging. And moreover, when we proceeded to the more advanced double tier, so-called Aridinus generation, the 5th generation, which has 2 different chips bump bonded together with an interposer, fortunately, the T1 and T2 were essentially unchanged. So that is encouraging. And in fact, we expect the T1 and T2 to both improve with further iterations. So where does the program stand now? We are several generations ahead of what I just told you about. We're now on the so-called Hydra generation. That is a 25 qubit chip. It's the world's first 3-tier high coherence 25 qubit quantum annealer. It has 40 couplers. It has individual high bandwidth control of every circuit element, which enables advanced annealing protocols. And it also has state-of-the-art readout using 25 QFPs, quantum flux parametrons, and tunable resonators. We've designed it in 2 different architectures, a square grid and a Kagome lattice. And this is now ready for basic science experiments. It's also on the cusp of being hard to simulate classically at 25 qubits. And we hope that it paves the path towards larger chips, hopefully 100 qubit chips in the not too distant future. Fortunately also, the chip is now cold in the fridge, and we expect it to be ready for science experiments when we finish calibrating it in about a month. Okay, so that is the survey of the QEO program, all I had time for today. And now I want to move on to part 2, which is a theoretical story. And it's about the critical evaluation of the adiabatic versus diabatic and the forward versus reverse quantum annealing approaches. So let me start with something very basic, just so that we're all on the same page. I want to briefly define what I mean by adiabatic quantum computing and quantum annealing in the closed system setting. So consider this the standard model. And AQC is a universal approach or universal model for quantum computing. As we all know, we start from an easy to prepare ground state, and then we find via adiabatic evolution the final ground state of a general Hamiltonian. In quantum annealing, as I'd like to define it for the purposes of this talk, the focus is on optimization. So it is less general. Now we start from the ground state of a transverse field Hamiltonian, Hx, and we solve the optimization problem defined by an Ising model on some graph via adiabatic evolution using the stochastic Hamiltonian that is a linear combination of the transverse field and the problem Hamiltonian Hz. For the entire talk, I will assume that we're in the stochastic setting, and there will be later talks today in the session about non-stochasticity, and I will not talk about non-stochasticity at all. So now it's worth noting that the possibility of efficiently classically simulating stochastic quantum annealing in the closed system case that depends strongly on the assumption that the system is at all times in a ground state of the time-dependent Hamiltonian, separated by a non-zero gap from the first excited state. And that begs the question, what happens if we relax this adiabaticity assumption of staying in a ground state and go to a model where we allow diabatic transitions? So this gives rise to two new computational models. One is the generalization of AQC, let's call it DQC. It will also be universal. And DQA, the generalization of quantum annealing. The D obviously stands for diabatic. So these are computational models in which at all times the system remains in a low energy subspace C of the Hamiltonian of width delta and dimension D greater than 1. D is the dimension of the subspace. All right, so schematically, there are some low-lying levels here that comprise the subspace C, and the horizontal axis is dimensionless time S. Transitions are allowed, diabatic transitions are allowed within the subspace, but transitions are suppressed by a gap delta to the orthogonal subspace, C-perp. So that's the diabatic model. And let me make two remarks. One is that in this model, we do not require the initial or the final state to be the ground state. And also, you might wonder, how is this model different from the gate model? And it's different in that we're going to insist that the dimension of the subspace is order 1, whereas in the gate model, the dimension of the space is the full Hilbert space, that's 2 to the n. Okay, so for this model, this diabatic model, what are the conditions under which such diabatic dynamics hold? And this is essentially the subject of the Adiabatic Theorem, even though we're talking about diabaticity. So let me explain. So definitions, as usual, S is the dimensionless time, and capital T is the total evolution time. Let's define the solution of the Schrodinger equation, the unitary U of T in the usual way, and consider the time evolved projection. P0 projects on the subspace C of interest. And let's also consider a projection on the low energy subspace at all times S. Okay, so now we're interested in the difference between this actual evolution, which is P sub T, and the desired evolution. And the adiabatic theorem, due to Janssen, Ruskay, and Seiler, which is stated here, essentially tells us the answer. It tells us that as long as the evolution time is sufficiently large compared to quantities like this, D again is the dimension of the subspace, times the norm of the derivative of the Hamiltonian divided by the gap squared at time 0, plus the same at time S, plus some extra terms, which I won't get into. So as long as the time is large compared to these quantities, then the system will stay not just in the ground state, which is the case D equals 1, but in fact within this subspace C that has dimension D. Okay, so this adiabatic theorem is actually a theorem about diabatic quantum computing or diabatic quantum annealing when the parameter D, the dimension of the subspace, is greater than 1. And this is encouraging because it tells us that the conditions for DQC or DQA are actually not harder to satisfy than for AQC or QA. The only difference really is this extra dimensionality factor, which we're going to assume is order 1. So it doesn't really change the hardness of satisfying the adiabatic condition. So now, so far I've talked about the closed system case, but consider also what happens when we have a bath. And let me talk about 4 different types of coherence in the context of adding a bath, of considering the open system. So the first case is actually when there's no bath, and that is just the fully coherent case, unitary evolution. In this case, the full power of universal quantum computing is unleashed. And of course, this is a great model to have in mind, but it's not very realistic. The second model of interest is so-called what I'm going to call the weakly decoherent case. In this case, we will not assume that there is coherence between eigenstates of the Hamiltonian. This is the weak coupling limit, or the WCL. We will assume that energy eigenstates remain coherent superpositions of computational basis states over a time scale longer than the total anneal time t. So no coherence between eigenstates, but coherence within an eigenstate relative to the computational basis. And in this case, quantum advantage is possible by remaining in the ground state. The strongly decoherent case is kind of the opposite limit. Now the energy eigenstates don't remain coherent superpositions over a time scale longer than t. This is the singular coupling limit. In this case, there's no hope of a quantum advantage, and I won't consider this scenario any further. And the final case is motivated by DQA. I'm going to call that C-coherent. So now consider coherent superpositions of eigenstates that are maintained inside a low energy subspace, C, over a time scale longer than t. But again, superpositions with energy eigenstates outside of C may decohere. So in this case, quantum advantage is possible by remaining in C. Right? So clearly, the C-coherent case is the generalization of the weakly decoherent case, where we're considering a subspace instead of just the ground state. So because the coherent and the strongly decoherent case are too extreme, I will not consider them any further. So let's focus on these two versions of coherence, weakly decoherent and C-coherent. And let's combine this with the dichotomy of adiabatic versus diabatic. And I would now like to start filling out this table where we'll be considering the coherent or C-coherent case versus the weakly decoherent case for both forward adiabatic and forward diabatic quantum annealing. And by forward, I mean the traditional scheme of decreasing A as a function of t and increasing B as a function of t. Okay, so let's start filling this out. And then when we're done, I'll talk about the reverse annealing version of this. But before I start filling this out, I just want to say that, of course, coherent or C-coherent is the case where we need some kind of error suppression. And I'm not going to go into it. There are references here which talk about how to enable this C-coherence using error suppression. And that's the subject of another talk. Okay, so with that in mind, that we can implement using error suppression techniques the ability to be in this row, consider first the case of forward adiabatic, coherent forward adiabatic. So the good thing is that we have the Adiabatic Theorem in this case with the standard version with the ground state only. And it tells us that provided we evolve the state sufficiently slowly, it will remain close to the instantaneous ground state. Another piece of good news is that there's a provable polynomial speedup, the work by Roland and Cerf on Grover's algorithm. But there is no known example of a provable exponential speedup in this setting. And generally, this setting is efficiently simulable by quantum Monte Carlo. Even though there are some counterexamples associated with topological obstructions and so on, generally it's true that QMC is efficient in simulating this setting of coherent adiabatic, forward adiabatic evolution. So I would conclude that this case has questionable promise. Next, let's talk about weakly decoherent forward adiabatic. So in this case, once again, there is an open system adiabatic theorem. And it tells us that the state for sufficiently long evolution times, the state will remain close to the instantaneous thermal or Gibbs state. So that's good. But there are no known examples of speedup. And once again, this is generally efficiently simulable by QMC. And the reason basically is that classical simulation by QMC involves two ingredients, which are both satisfied here. The Hamiltonian must be stochastic, and the system must be in an equilibrium state, either the ground state, which is the upper left corner here, or a thermal state, which is the lower left corner. So again, I would say this has questionable promise. Next, let's talk about forward diabatic in the weakly decoherent setting. So in this case, well, this first of all is essentially the original DWave setting. And we know that simulating the full open system dynamics is classically intractable for greater than about 20 qubits. And so whatever limited understanding we have of this scenario comes from experiments on the DWave devices and quantum Monte Carlo or spin vector Monte Carlo simulations. And indeed, the simulations correlate well with the experiments that were done on DWave. Now, unfortunately, as I've already mentioned earlier, QMC is efficient or scales even better, or scales better, even with thousands of qubits, as illustrated in this work. So that's not encouraging, although it should be mentioned that control noise could be playing a major role here. Also, there are no known examples of scaling speedups in this case, so I would say this too has questionable promise. So it's not looking good so far. But let's talk about the upper right corner now. So coherent or C-coherent forward diabatic. First of all, this is a scenario that enables universality. We know that AQC and excited states of stochastic Hamiltonians can be universal. We know that even a time-independent stochastic Hamiltonian suffices for universality via mapping to quantum walks. And we also know that simulating the full closed system dynamics in this case is classically intractable for greater than about 40 qubits. There are also numerical examples of a speedup over the adiabatic coherent case. So contrasting forward adiabatic and forward diabatic, there's an advantage being in the upper right versus the upper left. So one example is where DQA solves oracular problems with a scaling speedup over the adiabatic case. And specifically, this is known for qubit permutation symmetric problems, where C is the symmetric subspace with respect to qubit permutations. And so the cost function in this case is defined over bit strings, with the function here being only of the Hamming weight of a bit string. So one example is the so-called fixed plateau problem. The ground state is obviously where the Hamming weight is 0, or the all 0 bit string. And if you compare adiabatic quantum annealing versus DQA, what you find is that the time to solution for the adiabatic case scales like square root of n, the number of qubits. But remarkably, in the DQA setting, the time to solution is constant. It's independent of n. And that happens via a so-called diabatic cascade, which is a sequence of avoided level crossings, which is shown here for the fixed plateau problem. You can clearly see this line of avoided level crossings that eventually takes the system back down to the ground state. So that's encouraging. Also very encouraging is recent work on optimal QAOA, which is, turns out optimal QAOA is a bang anneal bang type protocol, which is very DQA-like. And I think we're going to hear a lot more about that in Lucas Brady's talk later in this session. So all in all, this upper right corner here seems to be promising. So to summarize, the verdict for the forward quantum annealing case is that coherent forward adiabatic is promising, but the other forward annealing cases face some serious challenges. Okay, so that's the forward annealing case. Now, what about reverse annealing? So for reverse annealing, let me just define the model first. I'm going to go through the same exercise of trying to fill out the table with reverse having replaced forward. So here's a schematic of a schedule where in reverse annealing, we start at s equals 1, go down, and then back up again. Whereas in forward, we just go from s equals 0 to s equals 1 with the possibility of a pause in the middle. So more generally, reverse annealing is a family of protocols that start from the ground or excited state of a diagonal Hamiltonian. They anneal to an off-diagonal Hamiltonian and then end with a diagonal Hamiltonian. And here are two important examples. One is so-called adiabatic reverse annealing, or ARA. And here the Hamiltonian is a combination of a diagonal HZ1, starts there, ends with HZ2, possibly different diagonal Hamiltonian. And in the middle, there is an off-diagonal component. And this is adiabatic, and that means we initialize in the ground state of HZ1. Then there's also iterated reverse annealing, or IRA. And here we start from a diagonal Hamiltonian and reverse anneal to an off-diagonal Hamiltonian. That's a combination of HZI and a transist field. But optionally pause, and then forward anneal to a potentially new diagonal Hamiltonian, HZI plus 1. We can iterate this. And for every I, we initialize in the ground or excited state of HZI. And this protocol is implementable on DWave. Okay, so now let's start to fill out the table. And let me start with the upper right corner. This is the case for which we have the first example of an exponential speedup in quantum annealing, except now I want to highlight that it is really in the setting of reverse diabatic quantum annealing, assuming C coherence. And the example is the well-known glue trees problem. I'm sure almost everyone here is familiar with it. You see this is a type of adiabatic reverse annealing between two diagonal Hamiltonians, H0 and H1. And in the middle, the Hamiltonian has this term, which is the adjacency matrix of the glue trees graph. What's remarkable about this problem is that it has a ground state and a first excited state, which are separated by, at first, a polynomially small gap, then an exponentially small gap. This is where diabatic transition happens. Again, a polynomially small gap. Again, an exponentially small gap where a second diabatic transition down to the ground state happens, and then a polynomially small gap. And the subspace C in this case is just the two lowest energy eigenstates. So it's been well established that this model exhibits an exponential quantum speedup, essentially for the problem of locating a path from the entrance to the exit. Okay, what happens when we, and of course I should say this means that this model is promising, the fact that we have a proof of an exponential speedup. Now what happens when we introduce a bath in this case? You can read about the details in our preprint, but it turns out that this still works for a sufficiently low temperature. So in particular, let's say that we want to prepare at all times the Gibbs state with inverse temperature beta. And let's assume that the temperature has this scaling given here. In that case, the distance, the trace norm distance between the final Gibbs state and the final ground state can be made arbitrarily small. So the story is, you see the 1 over n to the 4th here. As long as the temperature scales like 1 over n to the 4th, then the thermal Gibbs state is arbitrarily close to the final ground state. Right? So we don't need to do this at 0 temperature. Well, we can work in an appropriate weak coupling limit, and it still works. So we have an exponential quantum speedup in an interacting setting at sufficiently low temperatures for this model. In addition, of course, simulating the full open system dynamics in this case is classically intractable. And so with these observations, I would consider this reverse diabatic weakly decoherent case also promising. Next, we have the very recent result by Matt Hastings on a super polynomial quantum classical separation for the reverse adiabatic case. And I'm sure we're going to hear much more about this from Matt in session 3 today. But just very briefly, I would call this problem large cycle detection. Essentially, it's framed similarly to glued trees, where now the adjacency matrix is one of a different graph. And the computational problem is to determine a global property of this graph, namely, is a large cycle present? And what Hastings showed is that classically this takes at least n to the log n oracle queries, whereas the adiabatic quantum algorithm solves this problem in polynomial in n time. Again, this is done in the reverse annealing setting. There are some caveats. Both this algorithm and Grover and glued trees require many-body interactions. So they're more existential than implementable. They're not suitable in particular for quantum annealing with local Hamiltonians. So one might wonder what happens if you do impose the condition of a local Hamiltonian. And in that case, consider the Pspin model with adiabatic reverse annealing. So the model is one where the cost function is of this form. It's a trivial problem, computationally speaking. You can immediately see the answer. The ground state is the all zero state. But this is a model that is known to exhibit quantum phase transitions. And so it's interesting to try to see if the reverse adiabatic version can do better than the forward adiabatic version. And indeed it can. Let's introduce a diagonal Hamiltonian, an initialization Hamiltonian of this form, where the epsilon i's are chosen as plus or minus 1 at random, with C the probability of epsilon I being +1. And what you can show then through a mean field calculation, so this is not numerical, this is analytical. In the S lambda plane, S and lambda are the two annealing schedules here. You can show that for small c, small probability of epsilon being 1, there's a continuous line of first order phase transitions. But as you increase c, this line breaks, and wherever there's no first order phase transition, though the white space is second order phase transitions. In this case, first order phase transitions, as they usually do, correspond to an exponentially small gap. Second order transitions correspond to a polynomially small gap. So it makes sense to try to find a path like this purple one here that avoids, let's say for c equals 0.8 or 0.9, it avoids the line of first order phase transitions. This is not something you can do with standard forward quantum annealing, because then lambda is fixed at 1. And all you can do is go straight up the s-axis. In this case, you always cross the first order phase transition. So this is about avoiding a first order phase transition, finding a path that navigates around it by introducing an additional parameter in the adiabatic reverse annealing setting. And if you do this, then you can demonstrate numerically that the time to solution as a function of problem size goes from exponential in the forward quantum annealing case to polynomial in the reverse quantum annealing case. So that's an exponential speedup relative to forward adiabatic quantum annealing. The caveat here is that this requires a good initial guess, C, which is close to the ground state. And so it's not clear how well this generalizes to hard optimization problems. Nevertheless, I would say that in light of these results, the coherent or C-coherent reverse adiabatic case is promising. And that leaves us just with the weakly decoherent reverse adiabatic case, where we don't have too many results. We have some numerical results on an improvement that's possible over the closed system version. And I think I'm starting to run out of time, so I'll skip the details here. I'll just say that it's numerically possible to demonstrate an improvement over closed system. You see the success probability in a closed system Pspin model simulation with iterated reverse annealing versus the open system. Same problem, but now coupled to a bath, and you see how the success probability has increased as a function of inversion point, the point at which we flip the direction of the A and the B anneal schedules. So what's going on here is that relaxation helps. That's the bottom line. And that has also been shown in a study on DWave, where forward annealing was compared to reverse annealing. And without getting into the details here, you see the residual energy as a function of the pausing point. And for different initializations, if you, first of all, if you just do regular forward annealing, that's the dash curve. But if you do reverse annealing, iterated reverse annealing in the terminology I introduced earlier, depending on what your initial state is, if you start in the ground state, you do better than the forward annealing protocol. If you start in a higher state, then you don't. But iterated reverse annealing with an initial state that is the ground state itself does better than forward annealing for the same problem studied here, which was a 12-qubit small gap problem. However, it is the case that we haven't really changed the fact that quantum Monte Carlo is expected to be efficient in this setting, and that, of course, leads to some skepticism. So I would not rule out this case. I think it's worth further exploration because we don't have enough answers yet. So that's it. Let me now present you with the completed table, and you see that overall the reverse annealing approach, and specifically the reverse diabatic approach, has the most green in it. That's the last column. So I think that if we're going to focus our efforts on finding better ways to do quantum annealing and ask ourselves what the prospects are for a quantum enhancement using stochastic quantum annealing, that seems to be the most promising corner to focus on, with some additional possibilities elsewhere. Okay, thank you for your attention.
Thank you, Daniel, for this very nice talk. We started a little bit later, so we still have a couple of minutes for questions. Panelists can actually unmute themselves and ask directly. All the others, I think, should ask through the question and answer, or maybe I'm wrong. I mean, there is a difference between panelists and non-panelists, but I forgot. So please, okay. I think panelists can unmute themselves and they can ask. So any questions? Let's see if the question and answer has open questions. Not.
I'd like to ask a question, if that's okay.
Yes, of course. Sorry. Yeah.
This is Andrew King.
Andrew, please.
Hi, Andrew.
Hi, Daniel. I'm not sure how much you're able to tip your hand, but can you give us a hint as to the nature of the first things that you all will be exploring with the chip that's being calibrated right now?
Yeah, we want to focus on basic science experiments and explore in particular the role of coherence and how it interacts with small gaps. So we're interested in small gap problems that we've designed, and that will let us see whether coherence in these chips actually does what it's supposed to, which is enhance success probability for these small gap problems. So that's going to be the main initial focus. The particular problems that we're going to study have not been published yet, but I expect that they will be soon.
Thank you.
Okay, Daniel, there is a question in the Q&A by Viv Kendon. Do you have a sense of what practical noise levels are needed for C-coherent in relation to your latest QAO hardware chip? Can you read the?
Yeah, I'm not seeing the text, but what level of practical level of coherence was the question?
For see coherent
Yeah.
in
Right.
your latest hardware chip?
Yeah, so as long as we can demonstrate that the individual qubits have a T1 and a T2 that is of the order of the total anneal time, I think we should be fine. And the exact answer to that question is not known. I think that's open, but the answer that I just gave, I think, is a good rule of thumb.
Good. I think we are now, we should move on. So I'll thank Daniel again. Unfortunately, we cannot really clap. Okay, maybe I will. Okay, so
Thank you.
let's move to the second talk. Is Eleanor Riffel from NASA, half an hour, including a little bit of question possibly. Eleanor, do you hear me?
I can. Thank you.
Good. Please, you can start.
Can you see my slides?
Yep. Yes.
Great. Let me put them in full screen mode.
Fantastic. Okay, I will tell you when 25 minutes say are passed, so that maybe we can leave a couple of minutes for question. Okay, bye.
That would be fantastic. Yeah. So thanks to the organizers for inviting me. And I'd like to talk about the exciting next few years in terms of utilizing the devices we have ahead to get more of an insight into quantum algorithms. And sorry, there we go. So we're at a really exciting era where quantum supremacy has been achieved, but not useful quantum supremacy. There's the possibility of an early application to certified random number generation, but that's a very narrow application. And to go to broader things, such as the things that we're primarily interested in here, like optimization of various sorts and sampling and broader algorithms, it will be a while. So what can we do with these still limited devices, but that go far beyond what can be done in a reasonable time on supercomputers? And one is to do hardware investigations and noise, and that's very, very important. But I want to emphasize here the importance of doing algorithmic investigations, and also how these insights into algorithms can feed into the hardware and vice versa. So I'll be concentrating particularly on optimization and sampling for combinatorial optimization problems in machine learning, but there are other areas that are of great interest, particularly simulation of quantum systems. And unfortunately, there just wasn't time to talk about that, though we are starting to do some work on that at NASA, as well as lots of work in the broader community. So one thing I wanted to emphasize on the optimization and sampling side was that there are diverse optimization goals. You may be looking for exact optimization with guarantees. You may be looking for approximate optimization with guarantees that, for example, you're within a ratio of the exact ground state. You may just be looking for good heuristics without guarantees, but that generally do well. And you may be looking for fair sampling where you can get a variety of solutions, either in the exact or the approximate case. If, for example, you have uncertainty in your ultimate cost function or the circumstances under which your solutions will be deployed. And then there are various sampling goals, such as sampling from a thermal distribution. And a lot of what I will say can apply to all of these, but I don't want to, the more subtle aspects of these are very, very important when we're doing comparisons between algorithms, both between quantum algorithms of various sorts and also between quantum and classical algorithms. I want to really emphasize where we currently are on quantum algorithms. A lot of the hype and press coverage suggests that if we just have quantum computers built, that they'll be useful for anything and everything, and really do not understand that there's a lot of research still to be done on the quantum algorithms end of things. I think that's known very well to this community. But what I really want to emphasize is that this ability to play with quantum hardware, even with its limitations, allows us to do something that we really haven't been able to do much before, with the DWave being one exception to that. So there are provable advantages for, depending on how you count, a few dozen algorithms. We also know limitations, but for the most part, we don't know how quantum algorithms will affect certain applications. And at this stage of the technology, that is just not surprising, because if you look at classical computation, even for classical computation, it's hard to prove bounds on realistic cases. The analysis is just too difficult. And for a lot of the most complex computational problems, the best algorithms are just not known, and there's ongoing development of classical heuristics. And these are analyzed empirically. You run them and see how they do on problems of interest. And that's why there are, for example, annual SAT competitions, planning and scheduling competitions, machine learning competitions, et cetera, so that people can look at different approaches and see how they're faring. And it's only with quantum hardware that we can begin to play more of a role here. And really the next decade is going to be quantum heuristics coming to the fore. And the reason this is so important is that, just judging from the classical case as to where the algorithms for the hardest computational problems are, many of those are heuristic. And we will finally be able to really explore a wide variety of quantum heuristics coming forward. So I'm very excited about that and want to communicate that excitement to everyone here. And we'll now go on to talk about a specific case for these. And I'm going to talk both about quantum annealing and QAOA. And part of the motivation for that is that there's been a series of results showing connections between quantum annealing and QAOA, particularly between quantum annealing schedules and QAOA parameter setting. So, for example, Zhao and co-authors looked at a number of families of problems and found that for easy problems, QAOA schedules resembled adiabatic schedules. For harder problems, they resembled diabatic schedules. So very exciting in terms of tying these two together so that we can learn from quantum annealing something about QAOA parameter setting and vice versa. And Beng, Fazio, and Santoro also looked at these connections and found connections again between adiabatic schedules and QAOA. There had been an earlier result of Yang et al. On Pontryagin's minimum principle that implies that optimal evolution schedules may be bang bang, but if you look at it more carefully, for a fixed amount of time, the procedure has a bang bang schedule for part of the schedule at the beginning and the end, but more like a smooth annealing structure in between. So this is all very exciting, and I'm excited that I believe Glenn, I didn't actually hear the talk because it was in the middle of the night for me, but I believe Glenn talked about this briefly in his talk in the previous session, and Lucas will be talking briefly about that in his talk coming up in this section. Really exciting work. There are ties between all of these approaches to quantum optimization algorithms. We have a phase separation operator that's based on the cost function often just a direct translation of the cost function to a Hamiltonian, but also can include penalty terms to enforce constraints and some sort of mixing operator. Most often the transverse field, which is just the sum of the X operators, but we'll shortly see the importance of other mixers. So just to set the stage, I think everybody here knows about these different approaches. So in the interest of time, I'll just continue on. I'll give you a brief summary of Qaoa. It iterates between phase separation and mixing for P steps. And there are results showing that if P goes to infinity, it converges to an optimum, which is good. There were some exciting work for P equals 1, showing that it's hard to sample the output up to standard complexity theory conjectures, but that's a sampling, not an optimization result. Briefly beat the top classical approximation ratio for the problem of max E3 Lin 2, but then inspired a better classical algorithm, which is a win. But currently the quantum algorithm for just P equals 1 lags for by a log factor. And you may say, well, what about P equals 2? Well, so far the analysis has just proved too hard. And later results, we have a new algorithm for Grover's search problem that achieves the same query complexity, but is in the Qaoa setting. And if you just naively trotterize the Roland-Surf schedule for adiabatic optimization, for adiabatic quantum computation, you lose the square root speed up. So this is a non-trivial result, and also suggests that at least in some cases, you can find good parameters even for large P. So that's a setting. Now, we felt that it was important to generalize the quantum alternating operator ansatz to a case where not only do you have mixers which are beyond just the X mixer and allow mixing in the feasible subspace only, but also are closely tied with the ability to implement them on gate model devices. And so instead of just having e to the I beta k HM for some mixer, we're splitting this up into a bunch of HJs. We still have just one coefficient beta k for all of those HJs. You can think of the HJs as the gates that can be natively implemented on the hardware, so can take into account what specific gates are implemented and constraints on which qubits they can be implemented between. And that gives you a somewhat more general mixing operator. And you can write down, as we did, some desirable conditions for such mixers such that they provide non-zero transitions between all feasible states. There's more work to be done here, but that's this generalization is promising. You will always want to start the system in initial state, which is a superposition of one or more feasible subspaces and can be prepared efficiently. So you want to start in the feasible subspace. So just to give you more of a sense for this, there are many problems that have Hamming weight constraints on a subset of variables. I'll give you a simple example here, which is a max K colorable subgraph. Here, we want to properly color the edges, meaning that each edge, the vertices at the end of that edge should have different colors. We're going to use a one-clot encoding where there are NK variables, where a variable for a given vertex and color tells us whether that vertex is colored with that color or not. And we can then write the cost function as taking all the edges M and subtracting off the invalid, colors, the edges that have been colored with the same color at the end. And then we want to avoid invalid colorings where a vertex is labeled with two colors or not colored at all. We particularly want to avoid the second case where it's not colored at all, because a very easy way of optimizing this is to not color anything. So it's pretty important to make sure that every vertex is colored once and only once, and that gives us a Hamming weight 1 constraint. And under a normal transverse field mixer, you quickly lose that, even if you start in a state that obeys that constraint, you can quickly lose it. So instead, we want to use a swap or XY mixer that just swaps colors between at a vertex so that your vertices stay with just a single color. And so there are a few different possibilities there. You can order all of the colors and do a ring mixer where there's only swaps between adjacent colors, or you could do a complete mixer that swaps between every pair of colors, or something in between the two. There are a variety of possibilities. That's one of the interesting things here, and there are trade-offs between the implementability of these mixers and how much mixing they do. Similarly, for the initial state, we could do something very simple, like choose a feasible state, like all vertices colored red. That's very, very far from optimal, about as far as you can be, but at least it's feasible. Each vertex is colored with one color. Or you could do something like a superposition of all feasible states. So a W state for each vertex. That's a little bit more that takes more gates to implement, and so there's a trade-off in the performance. So lots of possibilities here, lots of work to be done. I'll just mention briefly that when you're compiling these down to specific gates, you may need to, because these more complex mixers, the terms do not commute, you need to pay attention to ordering constraints. If you did a whole global operator with all these XX plus YY terms all summed together and wanted to get that exactly, that would be very, very expensive to implement. But we can break these things down into, say, all of the odd ones and all of the even ones, which all of the odd ones commute with each other. So XX plus YY, where the first vertex is labeled with an odd number. So in that case, we can implement those in terms of gates fairly easily, and then just alternate between the two once or more times. These have the desired properties of a mixer in terms of like reaching all the feasible states, not going out of the feasible subspace, etc. And there's a lot of work to be done to understand where which of these are best, and it will depend somewhat on the hardware. We have numerical results showing the advantage of the XY mixer. This confirmed the advantage because basically you're maintaining the evolution within a feasible subspace. And it's worth noting that as the number of qubits increases, the difference between these two exponential subspace, the ratio between the two shrinks exponentially with n. So with larger numbers of qubits, one gets better and better results for the XY over just the X mixer. As I've mentioned, there are trade-offs between mixers and initial states. And we have a result that's coming out shortly on showing that the XY mixer retains advantage under noise, but that for all of these things, noise remains a problem. And one nice thing is that when you have symmetries like this, there may be some things one can do with error mitigation that, that can help you a bit. So look for that. We hope to have that out next week. And we have also looked at depolarizing noise in max-cut QAOA. I think that understanding the effects of noise on both the performance of the algorithm and how it affects the parameters is very important for research going forward. And again, it's not just for QAOA, it's also for quantum annealing because of the close tie between annealing schedules and QAOA parameter setting. So take a look at that. Further on parameter setting, there's discouraging results from the Barron Plateau paper. There's more promising results from the QAOA Grover's unstructured search, as I mentioned. For the trivial problem of max cut on the ring, it was surprisingly hard to do the analysis. The fermionic view helps, as we showed, and then Bang and others have been able to push that further. And there are other results. It's a very active area. Recent results of Bravi for getting the expectation value, for example. So I want to move on now to quantum annealing schedules. One thing that a number of us pushed DWave to do was to add a pause to the anneal. And the intuition here was not that you wanted to slow down right at the gap, which is what you might guess from adiabatic quantum computing, but rather that you want to slow down after the gap in order to allow thermalization. And what I really want to illustrate here is that there's differences between quantum annealing and adiabatic quantum computing, and also between open system effects. And you really want to look at what happens in the non-adiabatic regimes, and also what happens in open system regimes. And Zoe will be talking a bit more about this in her talk later. The theory has been pushed forward. There are recent papers, both of Tamim and Jeff, and also of Chen and Lidar, looking at understanding the theory of pausing better. And we have recent results that Zoe will talk about that show improvement in time to solution for a set of problems. But I'll leave that for her to go over with you. I also want to give a just hint at a different but very promising method here. And you can look at the energy matching problem. So given a classical state with a certain energy, it is generally hard to find another state with similar energy. And if this energy is up in a band where you have sufficiently many of these things, even if the probability of transfer is not high between far solutions separately, you can find enough paths there that you can get polynomial speed up in at least this random energy model. And a open question there was, when can you see that practically? So this is an asymptotic result, and when can you actually see this in practice? And Gianni will talk about this in his talk coming up. And what I want to emphasize here is the use of higher energy states in order to find, to solve hard problems. And not only does this affect the energy matching problem, but one could use this to do exploration in a higher energy band, and then use some sort of approach to, as you've moved further away, then do gradient descent or some other thing that can take you down lower to get an exact or approximate optimization algorithm into the lower energy states. So I think that this is a very exciting area that deserves to be explored more. And I also want to emphasize that for all of these things, it's really important to compare with classical optimization and sampling methods. And one of the things we've been very actively doing and working with a broader community is looking at what are some of the best classical optimization algorithms. As there have been advances on quantum algorithms, are there things we can do with the classical algorithms that can keep up with the advances in quantum algorithms? So for example, the isoenergetic cluster moves was one of them. And this is absolutely critical for us to continue to assess the quantum advantage here and to not fool ourselves. So just wanted to advertise that and to talk about that one of the exciting things coming out of the field is physics-inspired classical algorithms, as well as just a stronger impetus to look at classical algorithms for certain types of problems. with very novel techniques. And to emphasize that we really need to be careful in our evaluation criteria. So we should be comparing apples to apples. So if you have an algorithm that gives provable speed up, compare it to one that gives provable speed up or strong quantum speed up. Compare it with algorithms that give strong quantum speed up. And within numerical evaluation, you want to compare with the best approach, but look at whether they are tailored to the particular problems or not, because that can make a huge difference there. There's a lot of use for algorithms that are not so tailored and can be used generically. For example, often the problems we're looking at are subproblems that capture some aspects, but not all aspects of application level problems. And you would want to combine a bunch of those together. And so a non-tailored approach works for that. But tailored approaches are also, of course, very important for problems that when you want to solve the actual problem, as opposed to that just being a subset of what you'll ultimately want to solve. So with that, I want to give you some takeaway points. So what I really want you to take away from this is that there are a bunch of promising approaches in quantum annealing going forward. Daniel mentioned a number of them in his talk. We've also looked a little bit at reverse annealing, but he covered that very well in his previous talk. We looked at pause. There's just more control over annealing schedules is very interesting. More general mixers. I should have said that Itai Hen and Sarandri and Spedialeri also have suggested general mixers in the adiabatic quantum annealing setting. So there's synergy there. Also, the explicit use of higher energy states operating out of the non-adiabatic regime, where that may be explicitly helpful, open systems effects, ultimately perhaps going to engineered dissipation. We all talk about higher connectivity, more qubits, higher fidelity, et cetera, but I think these other aspects are really critical. Another thing I'd like you to take away from this is the synergies and even the blurring of boundaries between the gate model and quantum annealing approaches. So as I mentioned, there are strong connections between the two, but also in the hardware, gate model devices can be run in global modes. So for example, they can pulse between global Hamiltonians instead of breaking them down into 1 or 2 qubit gates. At least some of the hardware can be done in this way, which gives something between Qaoa broken down into gates and between standard quantum annealing. And similarly, quantum annealing schedules can mimic gate model schedules. Another thing I really want to emphasize is that while people are concentrating on building the universal gate model hardware, special purpose quantum hardware can play a really significant role in the NISQ era. We've already seen that with quantum annealers and how much insight they've given. More quantum annealing work with these more sophisticated approaches will tell us more, but there's lots of opportunities, for example, for going after something with the population transfer methods explicitly that I mentioned briefly and Gianni will be talking about further. Looking at special purpose hardware for specific algorithms or specific types of algorithms, for example, certain types of simulation. So real push to see a real ecosystem of quantum hardware here. And the importance of advancing classical approaches and doing the right comparisons here. And also just how exciting it is that we are getting to play with quantum heuristics in a regime beyond where we could simulate before, and how that will likely lead to significant broadening of applications of quantum computing. So I'd like to end with a historical perspective. Back in 1972, the director of NASA Ames at the time brought the ILIAC 4 to NASA Ames. The ILIAC 4 was the first massively parallel computer. And at the time, as the fastest computer in the world, it had a 50 megaflop peak. And it had 64-bit CPUs, and I'm not missing any Ks or Ms or anything here. This is really where the state of the art was. And when I first came to NASA, there were people in the supercomputing division who were very puzzled about these early quantum devices, such as the DWave machine. But a number of the older folks who had been around in the 70s came by and said, we know what you're going through. We had to find good problems that would show off the challenge, the promise of these massively parallel computers. And it was challenging because these are very limited devices, and people were very happy with, for example, their wind tunnel approaches. And so there were questions at the time as to what really will be the applications of massively parallel computing. And I think we all know the answer to that. And so if we in the quantum computing community can be even a fraction as successful here as they were with massively parallel computing, we'll have made significant contributions to the world. So I will end there, and thank you very much.
Okay, thank you very much, Eleanor. We are a bit behind schedule, but so in the question and answer, there is a question, will participant get this presentation? Yes, these are recorded. By the way, they will be shown again in the final session. Okay, this very presentation I think will be shown again, but they are all recorded, and I'm sure in the ICTP channel you can find all presentations. So if there is a very quick question, we can ask Eleanor. I see. Oh. No, I don't see any questions. Any questions from the panelists? Okay. Maybe we should move on. Now there'll be 4 focus talks. So they are 5 minutes long. So please, I would ask the person giving the talk to be quite sharp with their timings. Okay. So the first. So thank you, Eleanor, again for your nice presentation.
Thank you.
You can okay. We can start. We can start with the first focus talk, which is by Lucas Preddy from the University of Maryland. Okay, Lucas, please, you can start.
Okay. So you should be able to see my slides now. So I'm going to be talking about essentially the connection between quantum annealing and QAOA. And this is joint work with some of my colleagues at the University of Maryland and NIST. And let's get into it. So the problem that we're actually asking is we have 2 Hamiltonians. We're going to want to interpolate between them in some way, go from the ground state of this H0 to the ground state of H1. And the way that we can do that is with this control function U. You could split this into 2 control functions. For the purpose of this talk, it will be 1. There are other results if you have 2, but they're similar. And this is the format of quantum adiabatic optimization. This is the format of QAOA, annealing in general. And our approach is going to be to ask, what is the U of t that's optimal here for a specific tau, for a specific runtime? And the metric that I'm going to be using for optimality is the energy of the final state with respect to your H1, your final Hamiltonian. And as was mentioned before, there have been some results in the past based on Pontryagin's minimum principle that suggested that this was a bang-bang form. This is based off of the fact that in many classical problems, you get bang-bang as optimal. The translation from those classical problems to the quantum problems come with a lot of caveats, though. And the previous studies basically said that we don't expect those caveats to be important. Our work basically shows those caveats are extremely important and are coming up a huge amount in quantum problems. So don't have enough time to go fully through the proof, but to just give you a little bit of a flavor. Optimal control theory, all this is the calculus of variations. So we're saying that we want to minimize the final energy with respect to some control function. Our control function is the variational parameter that we're allowed to vary. And there are some other details, like you need to introduce Schrödinger's equation as a Lagrange multiplier. Going through, eventually you find that the variational derivative of the energy with respect to your control parameter is some function that we can calculate. Here, this is slightly different than the form presented in the paper, but in the Heisenberg picture with time-dependent operators, it has this nice form. And in the normal calculus of variations, we would say that we want this gradient, this variational derivative, to be 0 at a critical point. The problem is we're constrained. Our control function, we're only allowing it to go between 0 and 1. And this is just physical constraints of you can only apply your magnetic fields to a certain strength or something like that. And this modifies things. We might not actually be able to reach a critical point. So we have to say our gradient can only be greater than 0. So maybe if we're at the boundary at u equals 0 or u equals 1, we're going to do the best that we can, even though that's not a critical point. And this is all fully allowed. And in a lot of classical problems, specifically problems that are linear in the control function and the state, it's not possible for this phi, this gradient, to be 0 for an extended period of time. But in the quantum problem, it in fact is, but not everywhere. It turns out that at the beginning, you can prove that you have a u equals 0 bang, which corresponds to the problem Hamiltonian. And at the end, you have a u equals 1 bang, which corresponds to your driver Hamiltonian. And so the lengths of these bangs will be decreasing with your total runtime. And so in the limit of infinite runtime, you'll recover an adiabatic protocol again. But for shorter times, you'll have something more interesting. And in between, we have some analytics for what to expect, but you could get annealing, you could get bang bang. In practice, we've done a lot of numerics for Ising models, which is what I'm showing here, and we have a little bit for Heisenberg models. And the green here is the optimal annealing schedule that we get. And the blue here is the gradient. And red is I just took QAOA, constrained it to work within this amount of time and gave it, like, I think this was 15 or 20 bangs, told it to go to town, and it gets something that's essentially a trotterization of the optimal path. And just to this, both his results and as a useful toolbox, so just to give a very brief highlight of some stuff in the future, and this will be my last slide. We did a little bit of work this summer with a high school intern, Ivy, into what happens if your problem Hamiltonian isn't actually the one that you're trying to find the ground state of. And control theory suggests if you're trying to find the ground state of this Ising model, maybe you might want to look at these two other local Hamiltonians. And we have some results that say for very short times, you actually really want to look at this YZ Hamiltonian instead. Still, just using this Hamiltonian and your driver, not the original problem, and you might actually be able to go faster. But that's only for short times, and for longer times, you get back to what you would expect. So I'm done.
Yeah, thank you, Lucas. Thank you. So let's move immediately to the next speaker, Zoe Gonzalez Izquierdo, please. Zoe,
okay.
Can you hear me?
Hi, yeah.
Hello.
Yeah, I think I'm sharing now. Great. Hi, thank you very much for the opportunity to present here. And today I'd like to talk about our recent paper at Qaoa Group, in which we use a DWave quantum annealer to solve a class of optimization problems requiring embedding as a test case to investigate how posing affects embedded problems. So for the past few years, we've been able to have some control over annealing schedules on DWave. And the rate at which the annealing parameter S varies over time can be changed throughout the anneal. And it can be set to 0 for some time, which is what we call a pause. This pause can be located at any point in the anneal. Previous work has shown that a pause in an appropriate location can help boost the probability of success for native optimization problems. In particular, when a pause is introduced shortly after the minimum gap, where transitions to excited states are more likely to happen, we give the system time to thermalize. At this point, because the thermal state is, has a large overlap with the ground state of the problem Hamiltonian, we're more likely to end up in this ground state, improving the probability of success. So we want to extend this work to embedded problems. And we have chosen the class of minimum spanning tree with bounded degree problems, which have real life applications in the in robust communication networks. And they can be expressed as QBOs, and then they need embedding on a chimera architecture. So in our results, we will look at both the probability of success and the time to solution. We might choose parameters that increase the probability of success, but this usually comes at the expense of taking longer. So that's why we also look at the time to solution, TTS, which tells us how long it would take to solve the problem with 99% certainty. We will try to find parameters such as the pause time, pause location, and ferromagnetic coupling that will give us a high probability of success and a low time to solution. The ferromagnetic coupling is the coupling within a vertex model that is between qubits that represent the same logical variable after we embed. We're using DWave extended range for JF, the ferromagnetic coupling, where we find its optimal value, which is strong enough so that all qubits will remain aligned, but not so strong that changing configurations becomes too costly and decreases pre-success. However, when using this extended range, we can't do standard gauge averaging because this range is asymmetric. And usually we use gauge averaging to even out intrinsic biases by applying random unitary transformations. But that requires being able to flip the sign of the couplings, and we cannot do that when the range is asymmetric. So what we did instead was implement a new version of this method, partial gauges, and we simply apply gauges to all the other couplings outside of vertex models, which is equivalent to applying regular gauge transformations to the original problem before embedding. Both pausing and partial gauges improved our results for p-success. So here in blue, we see the results without gauges, and in green after doing 100 gauges. The horizontal lines correspond to results without a pause, so standard annealing schedule, and the data points to results with pauses at different locations. We see that, like in the native case, there is a window which we show here in which pausing improves p-success, and the optimal location is typically after the minimum gap. And normally, gauges don't improve p-success like this because we have some that are better, some that are worse, and after doing many of them, things will tend to even out. However, in this case, because our problems are very hard and p-success is close to 0, we won't have gauges that are very bad because we have a hard limit at 0, but we might have some that are really good, and this will improve our results. And that's why we see such a remarkable improvement between no gauges and 100 gauges. So in the previous plot, the ferromagnetic coupling was fixed to its optimal value. But if we vary it, we see that it not only affects p-success, but it also changes the location of the optimal pause. And this is because as we increase JF, the energy of the low-lying energy state increases, and this tends to shift the minimum gap earlier. And because the optimal pause location follows the minimum gap, we can see that as we increase JF, the peak in p-success shifts to the left. Finally, we want to improve not only p-success, but also the time to solution TTS. So for this, we will need to optimize all parameters, and in particular, choose pauses that are very short, around 1 microsecond. Here we show the instance-wise improvement in time to solution by introducing a pause for a few selected pause locations and durations. And if a data point is above 0, which as we can see all of these are, That means that introducing a pause improves the results for more than half of our instances. And the improvement is not as remarkable as for native problems, but is still statistically significant. The reason that is not as much of an improvement as for native problems is likely due to the fact that when we have an embedded problem, it is more costly to change configurations. So to wrap up, we have seen that embedded problems still benefit from a pause, although not as much as native ones. We can further improve our results by optimizing JF and using partial gauges. And the optimal pause location will depend on the value of JF. Looking ahead, we're very excited about the new advantage system from DWave and the Pegasus architecture, which will lead to a lower embedding overhead. And we can always look at new classes of problems and keep investigating how the annealing and embedding parameters affect their performance. Thank you very much.
Okay, thank you, Zoe. Let's move straight on to Peter McMahon from Cornell.
Great, thank you. Let me share the screen. All right, can you see this?
Yes, please. Yep.
Great, thanks very much. All right, so thank you to the organizers for giving me the opportunity to tell you about our work. What I'm going to tell you about today is a proposal that we have for a new architecture for how one might build a quantum annealer that is both fully programmable and has all-to-all coupling. And the kind of main technical technique we use to do this is Floquet engineering. So the main credit for this work goes to my co-authors Hiro Onodera and Edwin Ang, and this work recently came out a few months ago. And so the reference shown on this slide is where you can basically find out more about what I tell you about today if you're curious. So the main challenge we're essentially trying to address in our work is the challenge of connectivity in quantum annealers, and I think for this audience this problem really needs no introduction, but suffice to say that in most physical quantum annealers that exist at the moment, there is relatively limited connectivity between individual qubits, and if you would like to solve a problem that is fully connected or densely connected, you have some overhead because you need to do some mapping between the physical, between your logical spins and your problem you would like to solve in the physical qubits. And as a concrete example of this, in the DWave 2000Q system, the largest fully connected problem that you can solve or represent is one that has 64 spins. So there's some roughly order n squared overhead in the number of qubits you need to use to represent a fully connected problem. And if you only remember one thing from my talk today, it's that we essentially have a proposal for an alternative architecture for building a quantum annealer that attempts to address this problem. So there have been several proposals in the past trying to address this as well. A couple of them are shown on the slide. One of them is by Lechner et al. On the left. And you can see that in this scheme from Wolfgang and his co-authors, they still have n squared qubits that are being used to represent n spins, but in their scheme end up being able to represent the couplings or control the couplings using only local couplings. But nevertheless, there's still this n squared overhead. And in the scheme on the right from Nig et al., they have a much more favorable sort of scaling with the number of qubits. They only need to use n log n qubits to represent n spins, but there's a trade-off that's been made where now they only have n log n programmable parameters instead of n squared. So it's fully connected, but it's not fully programmable. So really what you would like is to be able to build a quantum annealer that is both fully connected, so every spin is connected to every other spin, and is also fully programmable, so that every spin you have, or every connection you have between pairs of spins is something that you can tune. And you would like to do this in a way that only uses n qubits to represent n spins, so having no overhead. We know how to achieve all-to-all connectivity. This is something that, for example, in the superconducting circuit community is well known. You can couple spins or qubits to a bus, and the bus will mediate interactions from every qubit to every other qubit when the qubits are all in resonance. But then the question becomes, well, how do you achieve programmability? So if you have a bus and you connect everything to everything, that's nice, but you still need to somehow program, or you would like to be able to program how those couplings are. And for this, we essentially took inspiration from the neuromorphic computing literature, where they've looked into a similar problem of how do you couple neurons via a bus, and how do you control things such that you achieve this full programmability. So our scheme is inspired by this, and basically the scheme we have settled on is having a bus resonator that couples oscillators. Each oscillator is a quantum oscillator that represents a single spin or a single qubit, and each oscillator is going to have its frequency modulated. And essentially what our paper tells you how to do is how to choose these various frequency modulations that you have to each oscillator, such that the net coupling matrix you get between the oscillators is the desired Ising matrix coupling matrix. Our scheme is fairly general. You can do it with a variety of oscillator systems, but an example of one you could do this with is Josephson parametric oscillators in superconducting circuits. We've validated the scheme using a number of numerical simulations in addition to analytics. And you can see some sort of flashed examples of numerical simulations here, where we have a 4-spin problem, and we're showing that if you have the perfect static coupling versus our dynamical coupling scheme, you're getting the same results. We've also managed to validate this with classical simulations so that we can go to much larger numbers of spins, up to about 50, and validated that it works. We've performed a scaling analysis of kind of what coherence time requirements you have. And the kind of key point is that at about 1,000 spins, we think that the required coherence time is going to be about 100 microseconds. So we think that this is a somewhat realistic architecture for superconducting circuit technology. So I'll leave you with the final slide. Thank you very much.
Thank you, Peter. Thank you. Thank you. So let's move to the final focus talk by Gianni Mossi from NASA. Gianni, please.
Yes, I'll go ahead. This is Gianni Mossi. Thank you for having me. I'm from NASA Quail, and I need to apologize to you, Giuseppe, because Antonello told me this was going to be a 20-minute talk, but I can make it way shorter. So this is the summary of a paper, actually a preprint that I've done in collaboration with Tommaso Parolini, who was an intern at NASA this past summer. Let's start from the beginning. The setup is combinatorial optimization. Typically in combinatorial optimization, you want to solve, say, a minimization problem over some binary string configurations. And through the standard approach, you can see that as the energy of a system of classical spins. Typically in combinatorial optimization, you want to find either the ground state of this system or an approximation of the ground state. We will focus on a different problem, which is the energy matching problem, which is considering that I'm provided with a state with a given energy that you must understand being some sort of approximation to a ground state, I want to find a different state with roughly the same energy. And this, as Eleanor described before, it's useful in general in cases you want to, in cases where you need more than one optimal solution or close to optimal solution. Ideally, you want to mine all of them. So this is not a very well studied problem in the literature. What we are going to do is to attempt to solve it through a method that was proposed, and it's called population transfer. I'll just go briefly to what the population transfer protocol means. The idea is that you prepare the initial state, the seed that you were given as a quantum state. You add a transverse field, then with a fixed value for the transverse field, you evolve the quantum system for a fixed time, keeping the transverse field fixed. So this is not annealing, this is not time dependent. And you measure the final state in the computational basis. And you will get a computational basis state with some probability. The idea is that you want to use the quantum resonant tunneling in a quantum dynamics in order to transfer amplitude within the same energy band. I'm not going to go through the justification from the physics, but you can see it from a kind of a Fermi golden rule approach. This is not a protocol we have proposed. This is some literature that came before, especially a paper by Baldwin and Laumann, as well as two papers now with Meliansky, Altschuler, and the Google group. on the impurity band model and the random energy model. In particularly on the random energy model, the analytics predicts a polynomial advantage of a random search, kind of a Grover speedup, a square root speedup. But these are asymptotic results, and so we were interested in seeing if this was achievable in the NISQ era. So what we did is to try and simulate this the dynamics on the random energy model. If you add a transfer field to a random energy model, you get a quantum random energy model, which describes the kind of quantum evolution, quantum propagation that the PT protocol uses. And there's some kind of some extensive literature on the quantum random energy model as well. It has a number of dynamical phases that will affect the population transfer protocol. For time restraints, I will skip the physical side of it, but I'll go immediately to the algorithmic side of it. So we want to compare population transfer with random search in the energy matching problem. So what can we do? There's some technicalities. We need to define what counts as the target states that you want to study, the energy shell. We fix the value of gamma of the transverse field, and we will study the protocol as a function of that. And the protocol is as such. The quantum protocol is, I get my seed, I run the PT protocol until saturation, until the delocalization process is complete. Then I measure in the computational basis, and I take the output as my final answer. In the classical case, the random search, I just discard the initial state and generate an output state at random. We study the ratio, actually the median of the ratios, the probabilities of successfully obtaining a state in the target band. And we see here, you see the finite size scaling of this. And you see that you have this kind of oracular gain. The gain grows with n, which means that the quantum PT is actually exponentially better than the classical random search. But the problem here is that we're not counting for the saturation time. So if you actually compute the saturation time, so the time for the PT protocol to complete, you see that that performs exponentially worse than random search. And you can see the details on the paper. We have some weighted performance measure. So essentially it's the probability of success divided by the time. And this is the ratio between the quantum and the classical one. And this is a battle of exponents that you see essentially sums up to 0. So PT and random search at these system sizes perform approximately in the same way. So, well, this is a kind of disappointing maybe, but I still think that the analytical prediction is correct. So essentially we see these as a finite size correction on top of that. So the main point here, the take home messages if you want, is that numerics will unlikely be able to study these kind of processes. So the development of dedicated analog quantum devices will be necessary to study population transfer and to see an actual speed up, because also gate-based quantum computation have a hard time trotterizing a continuous process. So with this, I finished my presentation. Thank you.
Thank you, Gianni. So we have eaten up part of the question and answer, but still a couple of minutes of urgent questions for focus talks. Please, any question? Question for the Peter McMahon talk. Doesn't the scheme suffer from frequency crowding? This is Alessandro Ciani asking. Peter.
That's a great question. Thanks. I was busy typing an answer, but I can just say it verbally. So yeah. Our scheme does suffer from frequency crowding, but in maybe a slightly different way than is normally the case, where I don't know if there is really a normal case for this, but what I think about is the normal case for frequency crowding is you have a bunch of oscillators that are frequency multiplex, and if you try to kind of use frequency as a way to sort of address which oscillator you're going to, for example, do a 1-qubit gate on, you need to separate the oscillators by at least the line width of each oscillator. Otherwise, you're going to accidentally drive the wrong oscillator when you think you're driving it. And this then leads to this sort of frequency crowding problem where you can't put too many into the window or the bandwidth of frequency that you have available for your oscillators. We don't suffer from that, or our scheme doesn't suffer from that particular problem, because each oscillator has its own independent control line, and so we can address each oscillator correctly. But we do still have a frequency crowding problem because of the essentially there's a limit to how closely you can space the oscillators, because the spacing tells you about how strongly things are going to couple, and also the validity of the Floquet analysis is affected by how closely the oscillators are spaced, and you can't go too close. But when we plug in numbers for kind of, well, how do we do when we imagine building this with superconducting circuits, and we sort of plug in how many are you actually going to be able to fit, we feel like we can reasonably comfortably fit 1,000 oscillators in the 5 gigahertz bandwidth between 5 and 10 gigahertz. And so if you wanted to take this up to 1 million oscillators, it probably wouldn't work. But we think up to at least 1,000, it seems like it should be fine.
Okay, thanks, Peter. If there is any other quick question, we can try to fit it in.
This is Daniel. I have a question
Daniel,
for
please.
Peter as well.
Yep.
Could you distinguish this scheme from the coherent Ising machine and talk a little bit about whether you expect it to ultimately be a quantum device?
Sure. So the scheme that we're proposing, and the work at least that I talked about in this talk, is very much in the sort of realm of quantum annealing in the sort of standard sense of quantum annealing, rather than in the sense of coherent Ising machines. Although there is kind of almost a continuum between the two things, because when you build if you build this with superconducting circuits, you can make them operate as quantum oscillators where the system truly is quantum coherent. And so it would be a quantum machine. And whether it is a quantum annealer in the traditional sense or not, basically will depend on the protocol you use of kind of how do you initialize your oscillators. But there's a very nice paper from Goto showing that there's a way to make something that is effectively a quantum annealer or an adiabatic quantum computer using quantum oscillators, where you represent the spins with oscillators. And there's also a bunch of work from Shruti Puri and Alessandra when she was in Alessandra Bly's group showing a similar thing. So I'd say you can make this a sort of to exactly follow the adiabatic quantum computing or quantum annealing protocols, but you can also operate it more like a coherent Ising machine. You can also imagine building this in a very highly dissipative system where it's not quantum at all, like the current optical experiments for coherent Ising machines. And well, the scheme would then be a classical coupled oscillator network system.
Good. Thank you, Peter. I think we should move on to the next invited talk by Andrew King from DWave. Andrew, are you ready?
I am here.
Okay, good. You can start. Okay, so half an hour including questions, okay?
Okay, thank you very much. And thank you to all the organizers. It's nice to be here, wherever here is for everybody. I'm going to talk a little bit about a couple of things that you can do with a new Advantage system. And I'm going to talk about what we've done with the previous generations of DWave processor and why we expect great things for the Advantage system. So already on slide 1, my information is out of date. Pegasus is now the current generation qubit connectivity, and Chimera is the previous generation qubit connectivity. So Advantage was put on the cloud last week, so feel free to go and check it out. In the current working graph, we've got 5,000, more than 5,000 qubits, something like 5,500, as opposed to 2,000 for the previous generation. We've got over 1 million Josephson junctions in this chip, and the maximum degree of the qubit connectivity graph has gone up from 6 to 15. So this allows you to embed things with less embedding overhead, as Zoe mentioned. And in particular, for the example of a 3D grid miner, where you could go up to 8 by 8 by 8 in the 2000Q system, you can go up to 15 by 15 by 12 in the current Advantage system. And furthermore, we have here, you can see you have these odd couplers. So the graph is no longer bipartite, which means that you can natively embed interesting non-bipartite systems. And so here, I'll excuse myself for the obscure link, but this is going to be recorded, so I don't feel too bad about it. This is a YouTube video on embedding things in the new architecture, and this is an archive preprint describing the new architecture and how to embed certain systems into it. And you'll note if you just look at the green qubits, for example, and delete the odd couplers, then you have a sub-chimera in the system. Okay, so what can you do with this graph? I'm going to focus on some finite dimensional systems that we have simulated in the previous system. And for all these except for one, the new system allows embedding with chains of length 2 instead of chains of length 4. So this started with Richard Harris et al.'s work on the 3D lattice. And we've studied a lot of two-dimensional systems in the meantime, including the Shastry-Sutherland lattice with Oak Ridge National Lab, quantum artificial square ice with Los Alamos National Lab, order by disorder and topological phase transitions in a quasi-triangular frustrated lattice. And one that nobody has looked at, as far as I know, is Buckminster-Fullerene, which you can actually embed with chains of length 3 in the DWave 2000Q processor. But in the Advantage processor, you can embed it without using chains at all. So I'll use this Buckminster-Fullerene as a nice example of important things that I want to communicate with people who want to do simulation of systems in the DWave processor. So the nice thing about having a non-bipartite graph is that you can put +1 on all these couplers, and because you have odd cycles, you have frustration. And so this is a Buckminster-Fullerene or a soccer ball graph, and all the cycles here have length 6 or 5. And one of the nice things about this graph is that it has tons and tons and tons of automorphisms, and we're going to exploit those automorphisms. So you'll note that each spin, I'll just separate these spins, the couplers by class. The blue ones are between 2 6 cycles, and the red ones are between a 5 cycle and a 6 cycle. So you have huge degeneracy if you just look at the antiferromagnetic case where everything is +1. You get 16,000 classical ground states. And in this Pegasus graph, you can actually embed 42 vertex disjoint copies using over 2,500 qubits. And you'll note that even though this seems like a sparse smattering of buckyballs, this is using more qubits than you had available in any of the previous processors. Okay, so back to the automorphisms, you'll notice that each spin is incident to 2 red couplers and 1 blue coupler here. And this graph is actually vertex transitive, meaning that there's an automorphism mapping this to this, any spin to any other spin. So if you take a soccer ball and you hold it such that some 5 cycle is oriented in some orientation facing you, you can do the same thing for any 5 cycle in any orientation, basically. And so this allows us to kind of study statistics of things that should be degenerate and sometimes are not. So I'm just going to use this as a canonical example, and I'm going to talk about some stuff that frequently or always gets relegated to the back matter of papers. And this is something that nobody really talks about very much in the front matter. And I think that it deserves a little bit more attention. So I'm going to give this a bit of a treatment. So there's been a lot of work on quantum simulation, and this has been the source of a lot of success with the DWave processors recently. And a lot of these simulations, especially when you're adding a transverse field to a well-understood classical system, this often relies on a classical system having very well-controlled degeneracy. And so you'll be familiar with the fact that whenever you have a calibrated system and you put an input on that calibrated system, you can sometimes change the calibration of it. So we kind of ship these processors with a one-size-fits-all calibration. And then if you're doing a simulation, you find yourself in a situation where you are spending a lot of time studying one system. And so when you're doing this, you can afford to make sure that everything is really well balanced. So for this example, I'm going to start by making sure that every qubit is balanced at degeneracy. So there's no H in this system, no longitudinal field. So we know that the observed magnetization of each qubit should be 0. So I'm just going to show an iterative method to balance the qubits. This is very simple stuff, and all we're doing is balancing out the crosstalk with a compensation. And if you Google this term flux bias offset, you'll find the documentation for the DWave processor if you're a user. So you initialize these offsets to be 0 by default, and then you iterate many times in a gradient descent method. So you anneal many times, and you can just average these samples that you get by spin, and you can look at the observed qubit magnetizations. You want these all to be 0, but they're not. And so what you do is you just update the flux bias offset on each spin by a step size multiplied by the observed magnetization. And I'm intentionally omitting the particulars of this because it's a general method, and you need to either fit your parameters properly or write a method that will fit it for you automatically, adaptively. Okay, so I'm just going to simulate the system again and again with whatever protocol I want. This happens to be a pause and quench protocol at s equals 0.4. And I'm going to show 300 iterations. So the first 100 iterations, I'm going to do nothing. And you can see that there are some systematics in the magnetizations that I'm observing. And then I'm going to turn on this gradient descent flux bias offset shim to balance the qubits to 0. And very quickly, we see these flux bias offsets jump away from 0. This is in microphi naught. And almost immediately, you see the systematic magnetizations that you saw in the first 100 iterations essentially disappear, and they're reduced to statistical noise or flux noise. So if you look at just 20 iterations here and 20 iterations here, so with and without the flux bias offset shim, you can see the histogram. This is all the qubits that we're working with, 2,500 qubits. And we expect these all to be 0, and they're really kind of spread out all over the place without the flux bias offset shim. And once we balance them with the flux bias offset shim, we get a really tight distribution. And this variance is essentially just statistical. If we continue doing this, we're going to get a tighter and tighter distribution, which basically becomes a delta function. So that's great. This makes our simulated degenerate system much more degenerate, and therefore we can observe quantum effects much more easily. And so I'm going to show the second approach, which is doing the same thing, except instead of balancing the magnetizations of the spins, I'm balancing the spin-spin correlations of 2 spins that are in a 5 cycle together. So I'm just going to do a coupler shim, and all of these start at +1. And for many iterations, again, I'm going to anneal many times, get observed spin-spin correlations for any 2 spins neighboring in a 5 cycle. And then I'm going to update the coupling between these 2 spins by a step size times the deviation from the expected value. Now, I happen to know the expected value, or the desired value in this case, because I very well understand the ground state manifold. But it's not necessary, because we're actually doing this for so many pairs of spins that you can just take the average over all these pairs. So you're just homogenizing these correlations, you're pushing them towards the average. And let's see what this looks like. So I'm going to turn on the previous flux bias offset shim that I already showed after 100 iterations. And then after 200 iterations, I'm going to show the coupler shim. So already just balancing the qubits individually at degeneracy reduces a lot of the correlation systematics that you see, but some remains. And then as before, this is almost immediately quashed by the calibration refinement. So these are the histograms for no shim, flux bias offset shim, and the full shim with both flux bias offsets and couplers. And now we're getting much, much better statistics. Okay, so this is a kind of a cute example of a fullerene, which is a system that we can't study in the previous processor. But I'm going to show an example of why this is really important for quantum simulation by way of discussing our recent result on a scaling advantage over path integral Monte Carlo. And Daniel mentioned this. It's a result on a geometrically frustrated lattice with cylindrical boundary conditions. And I'll describe to you what the experiment is in a moment. But what we end up with is we have two open boundaries here, and they're not actually the same as one another. You get these pendant spins on this side, but not on this side. And if we're really being faithful to the symmetries in this cylindrical boundary condition, the only sets of couplers that we can actually group together and say these should have the exact same statistics are rotational symmetry groups. So we partition the couplers into these rotational symmetry groups, and we do the same thing as before. We tune the couplers so that the spin-spin correlations within this group become tightly grouped around the mean. So just to recap this experiment a little bit, we first published the feasibility in 2018, and then more recently we published a rigorous benchmarking study of it against path integral Monte Carlo. So what happens is you get a quantum order by disorder phenomenon where you have a highly degenerate ground state in what is essentially a triangular antiferromagnet. And from this emerges an approximate XY model. And as you get these topological features like vortices and anti-vortices in this model. And as you lower the temperature, assuming that the transverse field is small enough that you're not beyond the quantum phase transition, you get long range order eventually. So in this experiment, we're not actually able to get long range order because this is much colder than the temperature of the system, but we can get to an extended critical phase where we see the onset of quasi long range order. And we can quantify the order in this system via an order parameter that comes from this pseudo spin over here. And you can see that as we sweep the annealing parameter S, this is very quantum and this is very perturbative, very classical. For the very quantum case where the transverse field is large, our estimates are totally out to lunch. And this is because the readout quench of the system is not fast enough for the dynamics in the system. So the system actually macroscopically orders during the readout quench. But as long as this slows down sufficiently, we can get good estimates. Now, this order parameter is just the magnitude of a complex order parameter. And we're going to measure this using a measure in the middle quantum evolution Monte Carlo method, where we do basically a Markov chain Monte Carlo. It's a non-Markovian Markov chain Monte Carlo, where each step is a reverse anneal. So we have a classical state, turn on quantum and thermal fluctuations, turn them off, classical state again and again. So we get a chain of observed classical states. And this is kind of in the interesting region where gamma is close to J. And if we take the average over many, many repetitions of this protocol, we can see the expected statistics after 1 microsecond of thermalization, 2 microseconds, 3 microseconds, and we can see the convergence from a number of different initial conditions that are based on topological obstructions. Qualitatively, the convergence from these topological obstructions is very similar to path integral Monte Carlo. You'll note that this is about 3 million times faster than a CPU here. But we're more interested in the scaling result. But let me talk about the symmetries that we want to see in this system. So it happens to be that this complex order parameter should be continuously rotationally symmetric in the large system limit, which we're close to being in, modulo our boundary conditions. And so this is what we want to see, and this is what we do see. In fact, this is the output from the DWave processor at high and low temperature here. And this is just a classic complex order parameter. And this is path integral Monte Carlo. So we're seeing the desired rotational symmetry, and we're seeing essentially not just the correct average magnitude, but we're seeing the correct histogram of magnitudes and phases. But what happens if we don't do the calibration refinement? So if we don't shim the qubits to degeneracy, and we don't shim the couplers to degeneracy, then what we get is heavily biased towards some particular phase. So this is a problem for two reasons. First of all, we're not getting the desired symmetries in the system. And secondly, this anisotropy that you get causes a drag on the relaxation. So you want to think about this like a kind of a glassy pond that you're applying quantum fluctuations to, and you need it to be really flat for the dynamics to be fast and accurate, for the equilibrium estimates to be accurate and the dynamics to be fast. But you see, you can shim away the individual qubit magnetizations very effectively, just like I did with the Buckminster-Fullerene. But this still leaves some systematics in the coupling. And then you can shim away the coupling systematics using these rotational symmetry groups. And you can see that the correlations, the AFM spin-spin correlations, become a little bit different as you get towards the boundaries. But this is actually correct. You expect them to be different as you get towards the boundaries. So this is something that we're not overfitting. So that's good. So I mentioned a speed up result, and the two parameters that we want to tweak in this case are temperature and system size. And so as you lower the temperature, the convergence gets slower and slower. The dynamics get slower and slower for both path integral Monte Carlo and quantum annealing. But for quantum annealing, the slope is much more gentle than it is for path integral Monte Carlo. And this is in line with certain theoretical examples where you can actually outpace the tunneling of path integral Monte Carlo using a quantum annealer in some idealized limit. But this is an experimental evidence of this. And I'll also note that the advantage that we see, this is just this divided by this. So it increases as we get colder, but it also increases as we turn up the transverse field. So the more quantum fluctuations we get, the higher the benefit from the DWave processor. And although we don't have firm evidence, one might easily imagine that this is because of extended tunneling range. So in terms of system size, computer scientists would be more interested in this, and you get more gentle scaling in the DWave processor than you do in path integral Monte Carlo. So you see a scaling advantage in both system size and temperature. So probably for this particular audience, people aren't going to be very impressed by 1,000,000 times speed up over specialized code in a CPU, because we've seen this kind of thing before. But what is really special about this, in my opinion, is that this is a real world application to the extent that computational condensed matter physics is the real world. And that means that people have actually studied extremely similar systems, and they've done so using path integral Monte Carlo. So we're really not just cooking up some fake benchmark here. And so this is experimental evidence that we've really wanted for a long time, that QA can beat QMC in scaling. Now, this is not, as Daniel mentioned, this is not for optimization, but I think that this is a really nice example because you can really see what's going on in the middle of the anneal under the hood. So we would expect even better results from Advantage. And we haven't had much time to play with Advantage yet, but as I said, this is one of the examples where instead of having 4-qubit chains, you can go down to 2-qubit chains. So I'll just use that statement to segue to a small performance example in Advantage, which is on 3-dimensional spin glasses, which Johnny mentioned as well. But we're not simulating these in the quantum system. We're just optimizing spin glasses. So this is a pretty basic experiment, proof of principle, basically, with this new processor. So both of these 3D lattices have the same qualitative embedding in both Chimera and Pegasus. So I'm just showing the 6 neighbors of a single lattice site here. So you have 2 in each of the X, Y, and Z dimensions. So this is Y, up, down, X, left, right, and Z, in, out, I guess. And these are 4-qubit chains, as seen in the Harris et al. Science paper. So in the advantage system, as I said, we can go up to 15 by 15 by 12, and we do so with 2-qubit chains with a qualitatively similar embedding. So just to go through this really quickly, looking at 100 random instances of each lattice dimension from 5 to 10, you can only go up to L equal 8 in the DWave 2000Q, and you can go up to 15 for the advantage processor, but I only went up to 10 for this particular example. What we're seeing here is the median and then 25th, 75th, 10th, and 90th percentiles of the 100 instances in these error bars. And you can see a pretty clear scaling advantage opening up over the previous processor. This is kind of almost an order of magnitude. And then in the 90th percentile, it's about 50 times improvement in time to solution. So what I've done is I've attempted to optimize the anneal time, but we can't find an optimal anneal time for the smaller instances. Looking at 100 random instances for 8 by 8 by 8, we can compare apples to apples. We've run the same instances on the two processors, and we see something that's very encouraging, which is that the advantage that we get from the new processor is the biggest for the hardest problems. So this is really encouraging for the kind of scaling advantage that we would want to see. We also see better consistency across cube isometries. So a cube has 48 symmetries or automorphisms called isometries. And this is an example where we're taking a spin glass instance. These are just plus minus 1 on the couplings, random bond model. And we're flipping this along the x-axis. So you can see that this is a mirror image of this one. And this allows us to actually run 48 different embeddings of each instance on each processor. This is 6 by 6 by 6, this data. And we can run fully yielded lattices on both chips. And you can see that not only do we see a scaling advantage for the new processor, the advantage processor, we see improved consistency with respect to these 48 isometries. So you see a much smaller variance. These error bars are the minimum and maximum for the 48 embeddings, essentially. And so this histogram shows the ratio of the best to the worst embedding. And you can see this ratio becoming smaller for the new chip, which is the kind of a consistency that we would expect from reduced embedding overhead. So I'll just touch on this very quickly because I've only got a couple of minutes left. This is a very recent collaboration with some people at the theoretical division at Los Alamos National Lab, where we introduced quantum artificial spin ice. For those of you who are familiar, artificial spin ice is a field of research where people essentially they literally fabricate frustrated magnetic systems using a variety of technologies, including lithographed nanomagnets. And so fine-tuning these is quite a lot of work. And we can do this reasonably easily in the DWave processor, given the appropriate embedding. And we can actually pin the boundary conditions in such a way that we can confine and study emergent monopoles. So one of the reasons why I want to show this, I'll skip over the details. We can see these monopoles walking around, but I just want to call out this system that we've embedded in the chip. There are a few defective lattice sites, and so these are represented by vacancies in the square ice system. So this system doesn't have any of the nice symmetries that I was talking about for the fullerene or for the geometrically frustrated lattice that we got the scaling advantage on. However, there's still kind of a get out of jail free card if you want to apply these calibration refinement methods that I've been discussing. And so the get out of jail free card is that you embed the system multiple times using local reconfigurations. And so even though this defective square lattice, it's a checkerboard lattice, it doesn't have any internal non-trivial automorphisms, you can actually map this 4-qubit chain to this 4-qubit chain in 2 different embeddings. And so that you can group and homogenize statistics by using that method. And that's a really nice way to get around this problem if you don't have symmetries in the actual problem that you're studying. Okay, so just to wrap up, I've used the fullerene example, which is a nice non-bipartite system that you can study in the Advantage processor to demonstrate some very basic and important calibration refinement methods that are really essential to getting good results out of simulation of highly degenerate systems. It's really important for suppressing crosstalk, and it's something that everybody does and nobody talks about it. So it's time to be open with each other and talk about how to get the best results here. And then just this 3D spin glass example is just a quick experiment that we've been able to do before releasing the Advantage processor, showing that these shorter chains yield better performance. And so there's lots of work to do. Please get on the system and help out. Thanks a lot.
Okay, thank you, Andrew. We're a bit behind schedule, but we started also a little bit late. So if there is any quick question, please ask from the panelists. Just unmuting yourself or all the others in the Q&A chat. Okay. Let's see. Okay. No questions.
Actually, if I may, I have a question for Andrew. It's Daniel here.
Yeah, Daniel, please.
Yeah. So Andrew, with regards to shimming, obviously this is something, as you say, you need to do all the time and you want to do all the time. Is it built into Advantage? Is it automated in some way?
No, it's currently not automated because the particular methods that you use for any given experiment, they tend to vary quite a lot. There would be ways of formalizing and automating it, but I think that probably doing so and getting the user to use these automated features, getting the right input for the appropriate automorphism classes, etc., would be just as challenging as cooking it up oneself. So it's something that we're going to work on, but I'm not sure how far we'll take it in terms of automation.
Okay. Other questions? If not, I think we can start with the recorded keynote talk by Hidetoshi Nishimori given this morning. So the next, say, 45 minutes will be this recorded talk. I think we can essentially say goodbye now. I remind you that in, say, less than 6 hours, there will be session 3, chaired by Nishimori. Okay, it's essentially in the middle of the night here in Europe, but it's a session for the US and Japan and Asia. Okay, so well, thank you to all panelists, to all participants, and I'll see you in a while. And I think we can ask the ICTP staff to start the.
We can start the talk. Thank you very much.
Okay, thank you very much for your introduction. I'm Hidetoshi, and I'm talking from Yokohama, neighboring city of Tokyo, indeed. So my topic is quantum simulation by quantum annealing. So let me share the screen for you. So this is the title of my talk. It's on. As probably many of you know, quantum annealing was designed as one of the methods to solve combinatorial optimization problems represented in terms of the ground state of Pascal Ising model. And for this purpose, we control coefficients of the transverse field Ising model appropriately to reach the ground state of the classical Ising model at the end of the process. So this was the original target, and this is the target as well, of course, now. But recently, an additional target of quantum simulation has been emerging very rapidly. And this is indeed a sort of real experiment on the chip of the annealer, DWave quantum annealer, more precisely. So this is a very exciting development, I think, because this is, in the first place, the dream of Richard Feynman to do quantum simulation on the quantum device. So let me list some of the recent examples of quantum simulation by quantum annealing. The static properties have been investigated on the spin glass problem in 3 dimensions, post-Star transition in 2 dimensions, spin ice problem, the Shastry-Sutherland model, field theory, Z2 lattice gauge theory, and Griffiths-McCoy singularity. And also dynamical or non-equilibrium properties have been studied on the quantum chip, mainly in relation to the Dirac mechanism and its generalization. And I will first review 2 of the previous studies, that is the Kostler-Thaler transition and the Shastry-Sutherland model. And after that, I will move on to explain our recent work on the Kibble-Dirac mechanism, generalized one, and the Griffiths-McCoy singularity. So the first topic is the quantum simulation of the Kostler-Thaler transition by Andrew King and co-workers, published 2 years ago in this reference. The Kostler-Thaler transition is a topological phase transition on the 2-dimensional plane for the XY model with continuous degrees of freedom on the plane. And those authors represented this problem in terms of the frustrated Ising model on the triangular lattice, for instance, the chimeral graph of the DWave chip. And as you see in these figures, for instance, there are configurations of the Ising spins up and down, and according to the configuration of these spins, they assigned effective spins, effective cluster vectors to the plaquettes on the triangular lattice. And those arrows can point to 6 directions, which is why this model is called the Z6 model. This is a discrete model because the spins can take directions only in 6 ways, but it is known that quantum or classical thermal fluctuations can erase effectively this discreteness in some parameter range. And they studied the ground state properties of this problem by quantum simulation using quantum annealing. And one of the typical spin configurations are drawn here. Spins point in various directions, and they appear vortices and anti-vortices. And the Kostler-Thaler phase transition is marked by the dissociation of these vortex anti-vortex pairs. And on this phase diagram drawn on the right bottom corner, which is drawn in terms of the strength of the transverse field gamma in this direction and the temperature. And it is known by quantum simulations, classical simulations by quantum Monte Carlo, that there are phases drawn here, ordered phase, in which the discreteness of the Z6 model cannot be ignored, and the KT phase, the Kostler-Thaler phase, in which this discreteness can be ignored, and paramagnetic phase, when the temperature of the transverse field are strong. And they traced, for instance, the system along this line on the DWave chip. So this line clearly hits the region where the system is in the costly Thales phase. And they measured various physical quantities, including the spatial correlation function. Here's the result, the distance and the correlation function. And this line represents the power decay of the correlation function within this region, which is a hallmark of the costly Thales phase. And away from this region, for instance here, the correlation function decays exponentially. So in this sense, they successfully reproduced the costly Thales phase transition by the quantum simulation. This is a very remarkable and interesting example of quantum simulation by quantum annealing. And the next example that I will review today is the quantum simulation of the Shastri-Sutherland model, recently put up on the archive by Dr. Keris and co-workers. So the Shastri-Sutherland model is a classical Ising model with strong frustration on the square lattice. J1 and J2 are both antiferromagnetic interactions on the square lattice. And Hz is the field, longitudinal field. Since both interactions are antiferromagnetic, this system is frustrated, and the ground state is highly non-trivial. And they simulated this problem by quantum annealing. And this is an instance of the behavior of the magnetization, longitudinal magnetization, as a function of the longitudinal field Hz. And it is known from theory that this magnetization has a plateau, one-third plateau, step structure in the zero temperature and thermodynamic limit. So this is a very interesting, unusual behavior of the magnetization. And the experimental results from the DWave chip are drawn in blue here. Since the system size is finite, limited, and the temperature is low but not zero, so this sharp step-like behavior is not exactly reproduced, but there are clear indications here and there that something singular would happen in the thermodynamic zero temperature limit. This way, they identify the phase boundaries here and there and plotted those points on this phase diagram drawn in terms of the longitudinal field Hz and the ratio of the interactions J2 divided by J1. And white lines are theoretical predictions, and red crosses are the results of the quantum simulation by quantum annealing. So the agreement is quite satisfactory. So in this way, they could successfully quantum simulate the properties of this complicated problem by quantum annealing. So such studies have been emerging very quickly in recent years. And our work lies along this direction. So let me introduce the first of our studies on quantum simulation. It is about the generalized Hilbert-Zurich mechanism. It's about non-equilibrium, diabatic properties of a quantum system, quantum phase transition. And this result is published already in physical review research. And this work was done in collaboration with a lot of outstanding collaborators. Bando, Susao, Shiyama, Shibata, Ozeki, Gomez-Luis, Lida, Suzuki, Del Campo. And one of the authors, indeed the first author, Yuki Bando, will give you additional information in this conference in session 3. So please listen to his talk. And this work is supported by the IAPA DARPA program. So what is the Hilbert-Zurich mechanism? it is quite a bit generic, general theory. But let me focus myself on the one-dimensional transverse field Ising model to be clear and to save time. So the program itself is very simple. It is a ferromagnetic transverse field Ising model. The state is ferromagnetic when gamma is very large compared to J. So in the limit of gamma infinity, the ground state is a superposition, equal weight superposition of all possible states into the L state. It is completely disorder. And as we decrease this ratio gamma over J very slowly, adiabatically, then the system will trace the instantaneous ground state according to the Adiabatic Theorem of quantum mechanics. And there's a critical point here, second order phase transition point here, gamma equal to J. And in the end of the process, when gamma reaches 0, the system is expected to reach the ground state of the trivial one-dimensional ferromagnetic Ising model, where all spins are either up or down. But if in practice, we change this parameter at a finite speed or in a finite annealing time, TA. So it necessarily happens that there exist some defects or kinks which separate neighboring domains of ferromagnetic phases, this and that. So this is an equilibrium or diabatic effect. So the program is to determine the number of defects n as a function of the annealing time, TA. If TA is infinity, then n would be 0. If TA is small, then n would be large. That is, n is a monotonically decreasing function we expected. And the Kibble-Zurek mechanism answers this question quantitatively. Please allow me to skip the details of the derivation because of the time constraint. And the answer is written in this formula. N is the number of defects divided by the system size, the chain length in this case, defines the density of kinks, rho. And Kibble-Zurek's theory predicts that rho is proportional to the annealing time, dA, to raised to the power minus d nu over 1 plus nu z, where d is the system dimension, 1 in this case, nu is the critical exponent of the divergence of the correlation length at the critical point, and z is the usual dynamical exponent. So our goal, our target is to test this prediction. And we know the concrete values of those critical exponents. First, if the system is completely isolated from the environment, there just exists the transverse field Ising model in the universe, then both exponents are known to be 1 exactly. So this exponent is 1/2, 0.5. But if the system interacts with the environment, represented by the bosons here, this is the standard form of the system boson spin environment, boson spin interaction called the Caldera-Leggett model, which is maybe called bit flip error because single z appears here. Then the critical exponents change according to extensive quantum Monte Carlo simulations by Berta and co-workers. And nu is changed from 1 to 0.63, and z is changed from 1 to 1.98. And those values, those new values, don't depend upon the strength of the interaction coefficients decay. As long as it is non-zero, those exponents stay stable. So this exponent with those values is 0.28. So we try to check which of those values are closer to the reality. And we run very extensive quantum simulations on the DWave machine, one at NASA Ames Research Center and another at Barnaby. And here are the results: the King density versus the annealing time in the log-log scale. Since this is a log-log plot, those straight lines mean power decay as exponent, as expected. And we excluded the data for the smallest, shortest chain, L equal to 50, because the number of kinks here and there are too small, and they don't satisfy the condition for the qubit direct theory to be valid. That is, the number of kinks should be at least one or larger. So we extracted the exponents only from larger chains, longer chains. And the results are 0.20 for the NASA machine and 0.38 for the Barnaby machine. So these values are to be compared with the theoretical predictions. As I explained in the previous slide, the theory for isolated systems predicts that the exponent would be 0.5. On the other hand, if the spin system interacts with the bosonic environment this way, then the theoretical prediction is reduced to 0.28. And clearly, the experimental values are much closer to the case on the left-hand side. Of course, there are deviations between 0.20 and 0.28 and 0.34. But those deviations come from non-universal factors, firstly because those two values are different. Those values depend on the machine, so it's non-universal. And non-universal effects may originate in various factors, such as imperfections in the manufacturing process in each machine, or different workings of the inverse noise in each machine. But the overall impression is that the experimental results are much closer to the theoretical prediction based on this type of system under the bosonic environment. So we conclude from the experiment on the average number of things that the DWave chips are under the influence of the bosonic environment. So this is the first result. And we also check the distribution of the number of things because we took a very large number of data points. In the previous slide, for each data point, for instance here, we took 200,000 samples. So we have this distribution function for each annealing time, EA. And Adolfo Del Campo, one of the co-authors of this work, developed a remarkable theory which predicts this distribution function. And according to his theory, which is based on the assumption that the spins or qubits are completely isolated from the environment. And he predicted that the ratio of the second order cumulant, that is the variance, to the first order cumulant, that is the average, is a constant as a function of the annealing time TA. You saw that the average kappa 1 depends on TA in power law. And the same is true indeed for kappa 2, but this ratio remains constant as a function of TA, and the constant is predicted to be 0.59. This is a very remarkable theoretical prediction by Adorko on isolated systems in one dimension. And the ratio of kappa 3, the third order cumulant, to the first order cumulant is also predicted to be a constant 0.13. And we tested this prediction from the DWave data. And we found very surprisingly that those data points lie on the theoretical prediction within the error bars. But we learned from the previous page on the average number of distribution, average number of kinks, that the chips, DWave chip, is clearly DWave qubits on DWave chip are clearly under the influence of bosonic environment. But experiment on the distribution shows that the result, experimental finding, agrees with the theoretical prediction for the isolated system. But we don't have a theory for systems under a bosonic environment. So we expect from this experimental finding that the theoretical prediction for isolated systems should remain valid, at least to a good extent, even under bosonic environment. This prompts a theoretical development for confirmation for this part, a theory for systems under bosonic environment. And we think this is probably the first time that quantum simulation has gone ahead of theory. So this, we believe, is remarkable in this sense. And as I said in the first part of my talk, that there are several studies on the Kibble-Zurich mechanism already. And I will review the recent work by Weinberg and co-workers in this reference. And they studied a two-dimensional problem instead of the one-dimensional case. And here is the result. This axis is the speed of change, which is inverse of the annealing time TA. So it's a bit confusing, but in a previous slide, we saw the axis this way. So the number of defects, this is residual energy, which is effectively equivalent to the number of defects. So the number of defects decreases as we increase the annealing time in this part, in quantitative agreement with a one-dimensional experiment. But they found a minimum for each curve, and this curve goes up again for long annealing time. And this part and this data, they analyzed by this phenomenological equation. And this first term represents this part corresponding to the Kibble-Zurich mechanism. And they extracted the exponent for this part from this fit, and the result is 0.74 plus minus 0.02. And there exists a theory for this two-dimensional case for a completely isolated system. And the theoretical prediction is 0.77, which is in good agreement with experimental finding. So it's a pass. In the one-dimensional case, we found that the chips, that DWave qubits are under bosonic environment. But in two dimensions, the experiment agrees with the theoretical prediction for the isolated system. So probably, I myself think that a theory for the two-dimensional system under bosonic environment, if it is developed, would lead to a very similar value for this prediction for the isolated system, but we don't know. This again prompts the development of a new theory. And also, in the one-dimensional case, we didn't observe such a minimum for each curve. So this part should also be resolved in the future. So this is our first result. And the second is about the Grips-McCoy singularity. It is a study done in collaboration with Koji Nishimura and Helmut Katzgraber. And it will be published shortly in Physical Review A, and the print is uploaded in arXiv. This work is also supported by Diabatic. So I first have to explain what is the Grips-McCoy singularity. So let's go back to the Grips singularity. Grips-McCoy singularity is for the quantum system, and Grips singularity is for the Pascal Ising model on the diluted lattice shown here. So consider Pascal Ising model on the two-dimensional square lattice, ferromagnetic interactions. But let's remove some of the interactions, dilution. Then isolate clusters with ferromagnetic interactions remain here and there. So the transition point, ferromagnetic transition point decreases from the value for the non-diluted system, TC star, to some value below it. And ferromagnetic order sets in below this TC. So this part, drawn in red, is paramagnetic. But Bob Griffiths predicted almost or more than 50 years ago that the predictability chi is singular as a function of the external field H, even in this paramagnetic phase. This is a remarkable result because something is proven to be singular in the paramagnetic phase. But this singularity is very weak, an essential singularity, as shown here, as written here, so it is hard to detect experimentally or numerically. And intuitive reason for this singular behavior is relatively easy to understand. In diluted lattice, there exist very large clusters here and there, although the probability for the existence of such large clusters is very low. The probability is very low, but they anyway exist. But since we are in the temperature range below the transition point for the pure ferromagnet without dilution, those spins in the large cluster respond very strongly to the external field. If the external field H is positive, even if it is very small, almost all spins will point to the up direction. If H is negative, even if it is very small, almost all spins will point down. So those spins for the magnetization changes almost continuously across H0. So this is the origin of this singularity, the Grips singularity. And this is the classical theory. And it is known that quantum mechanical system with transverse field, the transverse field Ising model also has this behavior of the singular behavior of the susceptibility in this parameter range, in which case this axis becomes gamma, the strength of the transverse field. And it is remarkably observed that singularity becomes much stronger in the quantum case because quantum fluctuations enhance the singularity. And although in the classical case, the singularity is very weak, in the quantum case, the singularity is strong in the sense that the linear and nonlinear susceptibility diverge in this parameter range between gamma C and gamma C star. So we checked if we can observe this singular behavior in the phasor two-dimensional diluted camera graph. And previously, there have been a lot of studies on this Grips-McCoy singularity on various cases. But studies of the two-dimensional randomly diluted ferromagnet have been rare. And mostly spin glass cases with plus and minus exchange interactions have been studied. And in particular, there has been no study for the chimera graph case. And of course, there has been no study by quantum simulation on the quantum device. So we chose this structure on the chimera graph. Some of the bonds are removed from the original chimera graph here and there, here and there. So this is the regularly diluted chimera graph. But this regular dilution doesn't affect the Griffiths-McCoy singularity. Only random dilution matters. And we chose this regularly diluted chimera graph because smaller connectivity is expected to lead stronger singularities in the case of the Griffiths-McCoy singularity. And in those remaining interactions, we introduced randomness in this case. Some of the bonds are 0, removed. Some of the bonds are 1. Some of the bonds are 0.2. So we observed the nonlinear susceptibility for this system. We observed also the linear susceptibility, but it is expected that the nonlinear susceptibility would behave in a more singular manner. The singularity is stronger for the nonlinear susceptibility than in the linear susceptibility. So we mainly measure the nonlinear susceptibility on the chimera graph. And since this is a random system, the value of this nonlinear susceptibility distributes. And it is known that by nonlinear, with large value, behaves in this Qaoa law. Don't mind the notation, it is just some exponent here. And from this distribution, we can calculate the average. And you see that if this exponent b over 3z prime is smaller than or equal to 1, then this average diverges. So what to do is to measure this distribution and check the exponent here to see if this condition is satisfied in the paramagnetic phase. So the result is here. This axis represents the nonlinear susceptibility chi and the distribution in the vertical axis. And we extracted the exponent by fitting the data to some linear curve in the semi-log plot, log-log plot, sorry. And those exponents are plotted as a function of the annealing parameter S star, which effectively represents gamma. And this is the critical point. And this part is the paramagnetic phase, and this part is the ferromagnetic phase. This is the critical point. And the exponents depend on the position in the paramagnetic phase. And those exponents, the values of the exponents depend on the way that we measure the value. But anyway, we think that the tendency is consistent, that this exponent will go below this threshold before the system reaches the critical point that is within the paramagnetic phase. We excluded the analysis, data analysis here, because the error bars are too large. Anyway, this quantum simulation has shown that nonlinear susceptibility is likely to diverge in the paramagnetic phase. This is consistent with the existence of the Griffiths-McCoy singularity on the chimera graph. And we carried out extensive quantum Monte Carlo simulations, which is the classical simulation, and backed up this result. So we think we have confirmed that the Griffiths-McCoy singularity is likely to exist on the chimera graph, diluted chimera graph. So, well, time is still 35 minutes, but I can conclude. First, we simulate an equilibrium dynamical phenomenon of the Hibble-Zurek mechanism and its generalization on the DWave chip. And remarkably, we believe that quantum experiment has gone ahead of the theory. That is, theory of qubits under environment should be developed to confirm the experimental finding that the ratios of the cumulant stay constant and the values are close to the theoretical prediction for the isolated system. And we also carried out quantum simulation by quantum annealing on the equilibrium or static phenomenon of the Pspin-Model singularity. And we found that nonlinear susceptibility is likely to diverge even in the paramagnetic phase on the diluted camera graph. And these results motivate further quantum simulations on the existing and future quantum annealers for discoveries or verifications of new and existing physics. Thank you for your attention.
Okay, thank you, Hidetoshi, for being on time for the great presentation. We have one question. By the way, let me remind you that the Q&A button where you can actually write your question is for questions regarding the talk. If you have technical questions regarding where to watch the video and so on and so forth, then you can email the secretaries. Okay, so there is one question by Nike Dattani, and it's about the simulation with the qubit with bosonic environment, and I will relate the question if you don't mind. So, how much does the exponent depend on the spectral density, ohmic, subohmic, etc., for the caldera-legged bosonic environment?
Okay, the simulation by Weinberg and co-workers were done only for the ohmic phase, and it is not known what will happen for the subohmic noise. So it is an interesting question. Yeah, but I don't know that.
There is another question, so let me just dismiss this. So there's another question. What about fermionic environments? I'm not sure if you can. If you can anyway.
Well, I don't know.
That they are difficult to
analyze theoretically and experimentally. Well, many people believe that bosonic environment is closer to the reality because it is harmonic. Smaller deviation from the ideal situation is represented by harmonic oscillators. But theoretically, it may be interesting to study fermionic environment, but no one knows for sure, to be honest. Sorry.
I do have a question actually myself, and it's regarding the nonlinear susceptibility that you spoke in. So if the exponent d over z prime becomes smaller than 0, then the probability distribution means that it's concentrated on the maximum.
Well, it cannot be smaller than 0.
Well, it cannot really be smaller than 0 because it would not be normalizable. It means that
So,
it's the maximum, right? Where the slope is now different, and everything is concentrated not around the typical value on the left, but towards a maximum value on the right. Do you observe anything like this? You said that you didn't.
Yes. In the ferromagnetic phase, we observe such behavior. Yeah, the distribution becomes flat, relatively flat.
I see. So if you believe that behavior, then there must be a point at which d over z prime becomes smaller than 3.
Yes, I don't say such such a strong word. It is consistent with the assumption that d over z prime is less than 3, because the data scattering is very large around here.
Yes, yes, yes. But even if, I mean, even if you don't trust the fit, if qualitatively the slopes are in the opposite direction, then you know, something must have happened in between somehow.
Yeah, yeah, of course, of course, of course. Yeah.
Say if the fitting function still works somehow in the
yeah. So it is an interesting question. It is very hard to extract a good amount of data from the DWave chip. Quantum simulation should be done if I want to answer that question.
Okay, I find it actually quite interesting that with the noisy near-term quantum devices, you can actually get such.
Yes.
I mean, this.
Yeah, this is one of the cleanest samples. I confess. You can check other set of data on the preprint.
I will definitely. This very much interests me. Okay.
Hello, everybody. Hello. I would like to thank everybody for participation and speakers for their talks, and see you in a while. Okay.